Steven studied networks, computer science at in Angers in France at an engineering school. However, he wrote his diploma thesis when he worked for Vector. And really, since 2008, he's been working on the subject of the Ethernet with Vector. So he's an expert on the subject. The floor is yours. Thank you. Welcome to my talk. I'm delighted to talk to you about our CANoe Ethernet solution. And I've structured my presentation into 4 different parts. So I'm going to start by talking about the evolution of the Ethernet in the automotive field. And then I'll briefly explain why we have come up with an Ethernet option for CANoe. Because it's not something that was to be expected, really. It's something that is actually quite old. And some other IT solutions are already available. And then I'm going to show you some CANoe screenshots. And I'm going to end my presentation today by describing a real use case from the field, something that we worked on at the beginning of the year, and which is really quite telling, which explains how CANoe can help to solve complex problems. So, what is the first important revolution, actually, that has been brought about by the Ethernet? As I said, the Ethernet is not exactly new. It's actually quite old. So it's used in the in many fields, but in the automotive field, of course, it's not used so much. Well, firstly, the network topology is completely different. It's not your classical topology that you know from automotive applications. So it's not a bus, nor is it a shared bandwidth. Rather, it's a switched network. So the advantages are that the bandwidth can be scaled. It's full duplex. So it doesn't use broadcast processes, but unicast and multicast. As I said, it's not about shared bandwidth. And as you can see here, if 2 here talk to each other, communicate, then only these 2 are actually sort of active, and the others will not even notice. So this makes it completely different from CAN, for example. What else is there? Now, the Ethernet is not a technology for a specific task. So really, you know, other things were developed for audio-video, for example, and CAN was developed for control and command. The Ethernet, however, is just a link, as it were, or one link in the chain. So the Ethernet could have a lot of physical layers. 100 base T1, for example, 100 base TX, that's almost Ethernet, then 1000 base T. And then there are also optical possibilities as a physical layer, or power line communication. Now above Ethernet, you can have IPv4 or IPv6 or AVB TSN, and at the top you have a wide range of different applications. Some IP, for example, for control commands, smart charging, diagnostics, or if you have safety-relevant applications, you could use the time-sensitive network, or for audio-video bridging, for example, too. Something else that is new with Ethernet is service-oriented communications, so the service idea. So the automotive industry hasn't been used to thinking in terms of services, but now here we're changing from signals to services and from fixed layouts for payloads to serialized payloads. And we're also going to switch from static to dynamic configuration by using what we call service discovery. And as I said, we are moving on from broadcast to unicast and multicast, and from cyclic to on-demand. So information will not be distributed to everyone, even to those participants who are not interested in information. Per unicast, only those will be addressed who have declared their readiness to take in this information. So only those who are interested. So what's the service discovery process like? It's quite simple. There's a client, a server. The server sends an SD offer regularly. And as soon as the service has made an offer, the client will know where the service is available. So it's simply an address from where a service can be reached. And when a client sends a remote procedure call at this point, and on the server then, the request will be processed, an answer will be sent back from the server to the client. So that's one way of, doing the communication here. And another one is this. The client in advance subscribes to the server. So it's like a kind of subscription, really. And as soon as that has happened, the server, once the information is available, it can actually send it out. The advantages of this solution are that you have higher flexibility, a higher rate of reuse, reduced bandwidth usage, and it also saves processing time of resources at the receiver. Now we'd like to address the question why we at Vector decided, yes, we need to have an Automotive Ethernet option. We think it would be good to round off our product. Well, firstly, Automotive Ethernet is really quite different from IT Ethernet, so there are some specifics to be aware of. It's got its own physical layer, 100 base T1. So that is something that you don't need really in the IT area. Then you need your own measurement interface. In the IT Ethernet, you have a lot of network technology, of course, but in a car, you have a lot of other bus systems. So it's a colorful picture: CAN, Lean, FlexRay, MOS, and things like that. And if you run a measurement, then you have to synchronize and log everything all of the time, and all of that highly accurately and with a timestamp. Because of the component test and integration, you also need simulation, and there are some real-time requirements. So we want to do fault injection too, and as I'd mentioned before, it's signal-based communication. In other words, unlike as is the case in IT, there is no exchanging of XML files between servers. So it's process data that are exchanged, speed, for example, brake pressure, things like that. And all of this is using the FibX and our XML database formats. So if you want to run Automotive Ethernet, then you have these database formats and don't have to worry about them. Now, our approach at Vector was this. We are going to provide a dedicated level. At this level, we'll have access to the customer to modify things, to extend things. And there are 3 important levels. To which a user will be given access either for analytical purposes or other. So there's a data link layer. So that's then at the transport layer. So that's with the UDP, TCP sockets, and at the application layer. That's our interaction layer. And this for different technologies like some IP, AutoSAR, AVB, or OEM-specific interaction layers. Next, I'm going to show you some CAN screenshots. And you can see our features there. We have our trace, for example, feature. So if you have, say, stored it in a database, it can interpret everything. Classical AutoSAR communication signals, for example, which haven't been visualized, or messages which transport serialized information, so which are more complex, too complex to be deciphered. What you can see here is that it was decided that we wanted to make this information clear to the user, customer. So that is why we introduced what we call a PDU view. Each PDU is a logical layer, an application layer. So each PDU has its own line or row, and then the trace makes it possible for users to filter. So what type of format or screen do they want to have? So at Ethernet, you have a lot of layouts. There's not just the frame layer, there's also the transportation layer, the application layer. And of course, depending on what it is you want to do, you have to choose the right format. So if you're only interested in application data, you should simply only show the PDU line and not the UDP frame, which only served as a container. But if something's wrong with the transportation, then you have to take the TPU or Ethernet frame to know where this frame is traveling to, from which MAC address to which destination address. Now, as we know it from other bus systems, so we have our graphics, and actually we support these new services too. So actually we support this in all the three windows you can see here. So this was for analysis purposes. This comes with CANoe. So there's also, however, the simulation side, screen in CAPL, and we've extended CAPL. So that's a new type of communication, such as some IP plus service discovery. So all of that can now be programmed, and this is what you see here. For example, we have on signals, you will know that from CAN and FlexRay. And all the service-oriented communication, for that, there's a new handler that is called on-service signal. You can use on-service signal update or on-service signal change. And basically, this works just like a signal, only it's got a different kind of qualification. So essentially, it's a different kind of communication. We also have our ILs, which just show you how you can do a remote procedure call, for example. So you can fill in a method, for example, and on the other side, you can then respond to such a request. So this is what we make available as part of CAPL. Of course, we have our panels too, and they too know how to process these signals. So this was for some IP and the control data. And CANoe, however, we also offer the possibility of audio-video streaming for analytical purposes, but also for simulation. In this case, for analysis, we've come up with some very interesting features. These generate a panel, and you configure the panel with the stream ID of the ID that you want to then have in your ABB network, and this will be done automatically by CANoe. It can sort the data in such a way that this data are then received, and it will then show the video stream. So it's a great feature, and it's fantastic to, well, have to quickly check, you know, how well your networks work. Now, and simulation. With our ABB interaction layer, we can model a CAPL talker, or sorry, simulate it or a couple listener. Now, for example, if you develop a talker and you need to have a simulated listener for it, you can do this very well with CANoe by adding an interaction layer. So what you do is in CAPL, you write, I want to simulate this stream, so there's a protocol stack which ensures conformity, then the streams are received, and then you can transfer that to the loudspeakers or into a media, or store it in a media file. You can also take the reverse route, however. If you look at the listener, you can simulate the talker. So with an input file, you can simply stream an audio file, and everything will be completely in conformity. Which brings me to my example or use case. It's a real example. At the beginning of the year, it was a problem we solved for a customer. A customer came to us and explained his problem this way. I've got a client and a server, 2 real control units. And they have been combined on a hardware in the loop application. Now, I cannot change them. They are linked through 100 base T1, and they exchange data, some IP, SD data, and some normal IP data per UDP or TCP. So what kind of data are they exchanging? Well, within the data, there was one notification which sent a GPS coordinate, and this coordinate was a string with a variable length, or that is what it was encoded like. And the problem was this. Hardware in the loop doesn't move. And of course, the client therefore didn't work, because the server gave it a coordinate which never moved. And the customer's idea was, well, I have a log file. I recorded that during a test drive, and what I really want is to change this coordinate. So these 2 ECUs, they should do what they did before, but somewhere in between them, something will have to intercept the coordinate and send on the position information. Well, the solution at a first glance seems rather simple. No problem, we do CANoe, and you can see the 2 ECUs. And then, in some way, we are going to manipulate the data. Now, the fact that we're going to put in a manipulating gateway between the 2 servers is really obvious. The question is, this manipulation, what is it supposed to do? Is it just about intercepting the frame and changing the signal, and perhaps to calculate a new CRC and then send that on? Well, unfortunately, the problem with this particular case was TCP. This coordinate was not sent by UDP, but TCP, and TCP secures this connection. So, what can go wrong? If you want to change a TCP stream, well, a lot of things can go wrong. And this is just one example out of many I could cite. So the ECU sends 3 bytes to the client. So in between, there's CANoe. It will actually intercept the 3 bytes and insert an additional one. Now we have 4 bytes, and these are then sent on to the client. So the client receives 4 bytes and sends an acknowledgement to the server about those 4 bytes. Now the server, however, knows or remembers it's only sent 3 bytes, so it will realize something must be fishy, dodgy. It doesn't really matter whether the CRCs were still correct. The server, the TCP IP stack of the server, it will realize that something wasn't okay. So you cannot proceed this way. It's not that easy. So what is the solution then? Well, basically, what we must do is that in CANoe, this TCP connection will have to split it, divide it into two. So rather than having C communicating directly with S, there must be a connection that is handed on to S. So it initiates a connection, but CANoe has to intercept it pretending it's C. And on the other side, it is building a new connection to S, and S thinks it's talking directly to C. So in order to configure something like this, the gateway has to offer a lot of functionality at all levels. Layer 2, the data link layer, data 4, the transportation layer, and layer 7, the application layer. So first of all, on the layer 2, well, all the packets which CANoe receives will have to be checked to find out, well, am I interested in this packet or am I going to send it on? Because if I'm interested in the packet, what am I going to do? Well, perhaps the MAC destination and the IP addresses will have to be changed so that the packet is rerouted no longer to S, but to some node in CANoe, which will manage this connection for me. And now, possibly because I use the TCP/IP stack, I'll have to do an ARP response and forge that. And at the transportation layer, I'll have to manage the two connections. And in the application layer, the data which we receive by the TCP socket will have to be unpacked. And I have to check whether I'm interested in the data. If no, I'll send them on to the other socket. Or if I am interested, then I'll have to extract it. So in this case, the GPS coordinate. I have to extract the coordinate and overwrite it. I'll have to serialize the data again and then send them on. A sequential diagram or sequence diagram of our solution looks like this. You've got a client and your server. Between the two, you've got the couple gateway. And the key characteristic of that is that it's got two another nodes, S dash and C. Well, S apostrophe and C apostrophe. And when the server talks to the client, the couple gateway will check, well, is this traffic I'm interested in or not? If yes, if it's a service discovery, then it doesn't have to interfere. It will just continue running. So everything that's sent from C to S and the other way will just be forwarded. However, as soon as gateway responds to a service discovery, if it realizes, well, the server gives me something that I need, then it will build a TCP connection to the server. And it's this connection which needs to be intercepted. So you have to pretend that S apostrophe is really S. And that will give you a valid connection on this side. So you have to make sure then that another connection will be open to S. Then S will respond because it believes that C has started to build a connection to it. And while it's doing that, we are intercepting this sync ACK. And then on both sides, we'll have a valid TCP socket connection. Then within that solution time, more data come in, let's say. But these are data that I'm not interested in. I don't really want the data. I'll just sort of look at them, find out, well, it's not something I'm interested in. I'll ignore it, and I'll forward it. And then finally, as part of this TCP stream, you will receive the coordinates which you want to change. So that is where you stop it, you modify the data, and then send them on. And in this case, as I showed with my example, you send 3 bytes and it receives 4 bytes. That's precisely what it's about. If you look at the coordinate, and you have fewer characters. Actually, here we added 2 characters, which means that this C here, this client now receives more bytes than were sent by S in actual fact. The good news about this is we managed to do the trick to get it right. It works. It's a problem that can be solved by CANoe. And it's a real application. It's running at somebody's factory or company. Customers have responded very favorably. S and C believe they're communicating directly, whereas in reality, of course, they don't. And it's only possible to do this because C and S do not identify themselves vis-à-vis each other. If they did, then this solution wouldn't work. So for the future, we can think about what would happen if all the end-to-end encryption, authentication, and encryption perhaps, if that is done, of course, it will be different because we need these applications, and all this encryption and so on, of course, will make this much harder. So, thank you very much for listening. Aufmerksamkeit is very hard to pronounce for a Frenchman, says the speaker. Do you have questions? Thank you very much for providing a glimpse with the, capabilities of CANoe today. Well, and you've heard today about a lot of different challenges, of course. Now, here we were looking at the man in the middle, the Ethernet. So let's see what will be needed in the future and what our customers expect and how they will use all of these things. Any questions? I can't see any hands in the air or requests for questions. Well, first of all, thank you very much. I'm Martin Hook of Vector Informatik. I'd be interested to learn more about the complexity of the gateway. How many lines of code do you need in order to provide this function? Can you give us an idea? Well, I cannot tell you off the cuff. Not so many capital lines, actually, just a couple of hundred lines of code or so. It's more the structure, so all the things you need to do. That is the problem. For example, which package do you have to intercept, which one to change, how to change it. And you don't need a lot of capital lines for that. It's more about how you actually do this. So the preparation for it is much more important. So it's CAPL that already provides the required infrastructure, right? Exactly. We've got the interfaces. As I said before, we have a data link layer, and we offer these Ethernet packages. So you can respond to all of these Ethernet packages. At other layers, you can manage the sockets. You can open them and then manage them. And then you've got the node layers and interaction layers, where data content, such as an IP message, for example, some IP message, for example, where you can extract data or set data. Here's another question. Maurice Wander of Porsche. I too have a question about your gateway example. What would happen in the case of a time-critical application, because the CAPL process is still based on a general unit, right? Good question. In our case, it wasn't a time-critical task. So we'd have to check that if we have a time-critical task. So whether we would still be sort of meet all the timing criteria. But, well, in our case at least, it was not really a noticeable effect. So in the future, any idea of what you might do? Because sooner or later you will have a problem with that. You mean in terms of time-critical tasks? Now, as a software engineer, I would say let's wait and see. If this really arises, then, if this case arises, then please talk to us. And, we weren't prepared here. It was a customer who called us and he said, I don't know how to, do it. And then we thought about the problem and whether it was possible, really. But then we came up with a solution. Thank you. Well, I think when it comes to a problem like this, you have to consider that you have a network here that has switches. So to expect from that system to exhibit time-critical behavior, I mean, the software to exhibit time-critical behavior, we'll really have to wait and see whether this is what will be implemented in applications. Now, I somehow suspect that it's not going to be the case, that applications like these are not going to respond to the delay. Now, if we're talking about just the normal Ethernet, really, I think some things will be added. And if you have a client-sensitive network, AVB, for example, generation 2, then that would infringe the time requirement because CANoe runs on a Windows operating system and it comes in, it won't work anymore. However, what we can imagine is that with CAPL on board, we can implement a solution like the one we described. As I said before, if you have a problem like this, then please get in touch with us and we'll find a solution for you. Well, we almost always find a solution. Well, like always. Thomas Biermann of Hella. Now, what you talked about was TCP communication. So the sender of TCP, it's got the MAC address, of course, and this needs to be mirrored back, of course. Now, the gateway, does it actually turn it around, or what does it do? Well, I simplified what happens here. What actually happens is this. Well, actually, I had expected that someone would ask this question. So they are not on the same net. So C and S are on the same subnet, but S apostrophe has its own subnet and C apostrophe too. So what happens in the background is that there's somebody who doesn't exist, and I take away his identity, I nick his identity. So basically, I change the data in such a way that S apostrophe believes that the information comes from a 3.5 node, but 3.5 doesn't exist. And as soon as S apostrophe responds saying, well, 3.5, what is your address? Then I have a code which does this kind of spoofing. So it states an address, then it will write back. And once the sync ACK is sent back, in my code, the IP address and the MAC address will be exchanged. So basically, C never knows that it hasn't communicated with S. And this also applies to S, of course. You can only know when you're in CANoe, because CANoe will show you the traffic and how it's modified or changed. But if someone was to connect with an analytical tool like CANoe, then it would see, well, here and here there are 3 bytes, and over there there are 4 bytes. And in spite of that, there are no faults. Neither the server does a retransmit, nor does the client say something's wrong. So that would look funny indeed, and it is a bit funny, really, what's happening, because of this magic I explained. So it's all about spoofing, lying, deceit. Well, just like in the real world. So authentication is not a bad thing, really. Authentication is not a bad thing. Just shows what we're capable of, said the moderator. Any more questions? No questions have come in through WhatsApp, I believe. So, thank you very much then.